Good morning, everyone, and welcome back to this series of courses on Analysis 2. I'm Dr. Achouak Bekkai, and I'll be your instructor for this course at the University of SoukAhras. I'm excited to guide you through the fundamentals of Analysis 2. Now let's dive into the course content. We'll start exploring the key concepts and topics that will shape our understanding of Analysis 2. The course is divided into three main chapters. The first chapter covers the basic ideas of limited development. The second chapter is devoted to the study of primitive functions, as well as the methods and techniques of integration, which are essential in all integral calculus. Finally, in the third chapter, differential equations and their resolution methods are introduced, as they have various applications in diverse fields such as physics and engineering. Let's begin with Chapter 1, Limited Development in Physics and Mathematics. A limited development of a function at a point is a polynomial approximation of that function in the neighborhood of that point. This means expressing the function in the form of the sum of a polynomial function, a negligible remainder in the neighborhood of the point considered. During this chapter, we will explore 1. Comparison relationships, 2. Limited development in the neighborhood of a point, 3. Taylor's formula, 4. Limited development of usual functions, 5. Operation on limited development, 6. Limited development at any point, 7. Limited development in the neighborhood of infinity, 8. Generalized limited development. Finally, some applications of limited developments. Limited developments are very useful for finding the limits of functions, studying indeterminate forms and position of a curve relative to its tangent. Many problems require that we recover a function from its derivative, or from its rate of change. For instance, the laws of physics tell us the acceleration of an object falling from an initial height, and we can use this to compute its velocity and its height at any time. More generally, starting with a function small f, we want to find a function big F, whose derivative is small f. If such a function big F exists, it is called a primitive of small f. This is what we will learn in Chapter 2, Calculation of Primitive. We will start by providing some definitions and properties, with some techniques of integration, as we will see the integral of certain functions as rational, exponential, and trigonometric functions. Now let's move on to Chapter 3, Differential Equations in Mathematics. A differential equation is an equation that relates one or more unknown functions and their derivatives. In applications, the functions generally represent physical quantities, the derivatives represent their rates of change, and the differential equation defines a relationship between the two. Such relations are common, therefore, differential equations play a prominent role in many disciplines, including engineering, physics, economics, and biology. This chapter will cover some definitions, and we will focus on first-order differential equations and second-order linear differential equations with constant coefficients. Let us now study a type of first-order differential equations, called differential equations with separable variables. The technique of separation of variables involves rewriting the equation so each variable is only on one side of the equation. So x is on one side and y is on the other. If a differential equation can be solved by separation of variables, it must have the following form. We want the x's on one side and y's on the other. Then we can integrate and find solution to the differential equation. Bernoulli differential equation is known as the Bernoulli differential equation in honor of Jacob Bernoulli, a Swiss mathematician who made a significant contribution to the derivation of the equation. Bernoulli differential equation is one of the topics that fall under calculus and differential equations. It is a nonlinear differential equation of a specific kind that can be transformed into a linear differential equation through substitution. It is defined as, where a and b are two continuous functions of the variable x, n is a real number not equal to 0 or 1. To solve a Bernoulli differential equation, follow these steps. 1. Let's divide both sides of the equation by yn. Substitute z equals y1 minus n. 3. Rewrite the equation in terms of z. 4. Solve the resulting linear differential equation. Finally, thank you for your attention.